Hey everyone, welcome to AMSA UCF's first ever web series workshop. We're super excited to get started with the web series this semester. This has been something that we've been wanting to do for a while, but really haven't had the bandwidth to go ahead and work on. So we're super excited to get started this semester with our first workshop today being Intro to Python for Data Science. In today's workshop, we hope to give you guys a little bit more familiarity with Python, specifically for your data science projects. With that being said, we are going to be going through this workshop with a little bit of like a prerequisite understanding of maybe some basic programming knowledge. So think maybe another language like C, C++, or Java. But even if you don't have that prerequisite experience, this should be relatively straightforward and easy to follow, and we'll be very granular in how we go through each of the steps. So it should be relatively easy for you to follow along even if you aren't super familiar. So yeah, with that being said, we'll go ahead and jump right into it. So the first thing I'll point out is that we aren't in a normal Python script file here, right? We're not in a .py file. And the reason for that is that in data science, we typically leverage what's called a Jupyter Notebook for a lot of our data exploration and sort of preliminary testing and modeling. What is a Jupyter Notebook? So a Jupyter Notebook is, as sort of the name entails, a notebook for you to be able to show your Python, Julia, or R code alongside certain text blocks. So it allows you to run your code, visualize your data, do some preliminary modeling, but in a way that isn't running all in one sequence, right? So it allows us to break it up in a little bit more of a convenient manner. So that's why we're going to be using it today. So you'll see today in the file name, it has this file type IPYNB. That just indicates a Jupyter Notebook. So that's some important knowledge moving forward in your data science journey. And again, just some more housekeeping stuff. In the description of this video, you'll find this python for ds.zip file. I encourage everyone watching this video to go ahead and download that. Once you download it and then extract that file, you'll get this folder, which is just Python for ds. When you open it, you'll see three files. You'll see blank Python for ds.pyynb, completed Python for ds.pyynb, so both of these are Jupyter Notebook files, and you'll see housing.csv, which is the data set we're going to be using a little bit later on. CSV just means comma separated values, so think like tabular data. So to speak a little bit more on these two Jupyter Notebooks, so this blank Python for ds file is what I have open back here, which is just all of like the headings and all of that and all the formatting set up, but with none of the code actually written. We'll be going through and filling that out throughout the remainder of this video. So if you want to go ahead and use that one and follow along and code alongside me, you're more than welcome to. And we have the completed Python for ds and Jupyter Notebook, which is the completed Jupyter Notebook with everything pre-filled out. So if you just want to go ahead and reference that as you work on your future Python projects, or if you just want to click through and sort of play around with the code on your own, you're more than welcome to do so. With that being said, just one more thing, I do want to mention the platform that I'm using to work on today. This is a website called Google Colab, which is one of the ways that you can work on a Jupyter Notebook file, among many. And the reason that I chose to work on this is it's very likely the most successful way to use a Jupyter Notebook. All that's needed to create a Google Colab file is a Gmail account. And if you're watching on YouTube right now, you presumably have a Gmail account. All you need to do is look up Google Colab, create a new file, or import the file from the .zip that I have in the description. And you should be able to follow along using Google Colab. If you have it set up locally and you don't have to create any new environments, feel more than free to do so, but this is just the easiest and most quick and accessible way to sort of get into a Jupyter Notebook environment. With that being said, we'll go ahead and get started with the actual coding bit of this workshop. So the first section that we have here is data types. So if you've worked in any other programming language like maybe C or Java before, you might be familiar with declaring variables in kind of a more systematic manner, right? So maybe you have an integer x and assign that to, let's say, 5, right? So what's important here is that you're defining not only the name of the variable, so in this case x, and not only the value of that variable, which in this case is 5, but you're also specifying the type of that specific variable. This is something that's a little bit more unique about Python. When you're defining a variable in Python, let's say that you want to define that same variable, you're going to define it as x is equal to 5 without this first type hint, right? Reasoning for this is Python is what's called a not strongly typed language, right? So languages like C++, C, and Java are what are called strongly typed languages. So you have to explicitly define the type of the variable as you're defining it, right? It leaves less room for sort of this clean syntax, right? Reasoning for that is because Python behind the scenes will sort of interpret the variable that you're defining and sort of assume a type at runtime. You don't really need to understand all the ins and outs of that, but you just need to understand that you're not going to be explicitly defining the type of the variable, and that you need to be mindful of the types that you're assigning, and that you're not creating any potential downstream issues later on by not defining the type explicitly. To kind of go through the rest of the types that we have in basic data types, we have the integer, we have a float, so let's say 2.2. Again, define exactly the same as the integer, except we just have to pass in a non-integer. So in this case, we passed in a float. So we can call this a float. Then we have strings, so we can write this as s is equal to, let's just say, hello world, which is a string. Important note here, you'll notice that in Python, in this first example, I assigned s to be double quotes in hello world, and then double quotes again. Interestingly enough, you can actually do the same thing with single quotes. If you worked in other programming languages, these single quotes typically denote a char data type, but in Python it's a little different. Both of them are strings. There's not really much of a difference, but just something to kind of keep in mind is you can use them interchangeably. And then the final data type that we have, is of course booleans, which are just true or false, right? So this is just a boolean. So yeah. Kind of important to keep in mind that these aren't going to be strongly typed, but the variables in the way that they work in Python are relatively simple, so not too much to learn here if you've had any non-zero amount of programming knowledge in the past, right? In terms of printing, again, in Python, printing is really simple. All you have to write is print, then you can pass in anything that you want to print to the screen. So let's say we just want to pass in hello world. And yeah, we can go ahead and print hello world. Well, I guess something we should maybe discuss a little bit is when we want to print out like a variable, specifically when we combine that with text, right? So let's say we want to print out x is equal to, and then we want to pass in the value of x, right? The one way that we could do this is that we first have this string in the print statement, comma, and then we pass in the variable x, and we see that passes in x is equal to 5. There's a slightly more elegant way of doing this with what's called an f string or a formatted string. So how this would work is that you would type in the same statement, print, and then before you start the string, you type f, then you can start the string. You can say x is equal to, and then in curly braces, you put that x. So you can see the output is exactly the same as before, but instead of having to put the comma outside the string, we can sort of just pass in the variable right in the string itself, which is a little bit more elegant, right? So something to keep in mind. Multiple ways to do that. Again, kind of comes down to personal preference, but I think this is generally the more accepted way of doing it. Cool. Now we can go ahead and just talk about operations. Again, kind of what you would expect for the most part. If you want to do 2 plus 5, all you have to type is 2 plus 5. Conversely, 5 minus 2, that's going to get you, obviously, it's the same thing. And then we have multiplication, so 5 times 2. Again, behavior exactly as you'd expect. Division is where things get a little bit tricky in Python. Typically, when you're working in any other language, when you write 5/2, you'd expect it to do integer division. So you expect the output of this to just be 2. But in this case in Python, it's actually doing float division. So you get 2.5, which is what you'd expect in like normal arithmetic, right? Reasoning for this is because Python actually has 2 ways to do division natively. So we have this first way, which is what you would normally expect, and then you can also do 2 slashes, and this is what's actually going to give you integer division. So this is just something to keep in mind. Python gives you a lot of access to do both of these types of division when you see fit, but it's really easy to get mixed up, right? Again, since types in Python are not strongly typed, it's very easy to accidentally do the wrong type of division, and then you accidentally have a float when you want an integer, or conversely have an integer when you want a float. This can cause some downstream issues with some type hint, because of the lack of type hinting. So it's very important to keep in mind what you want to do and how you need to be doing it. Something to keep in mind. And the last one is exponential. So if we want to do like 5 squared, it's 5, then 2 asterisks, and then the number that you want to raise to 2. So in this case, 5 squared, obviously 25, right? But yeah, apart from that division thing, operations in Python are pretty standard. Not really much going on there. Now we can go ahead and talk a little bit more about data structures. So data structures in Python are relatively simple. So the first thing that we have is obviously the array, or Python calls it the list. there's some like technical nuance between what's an array and what's a list. I'm going to be using them interchangeably because it's not really super important in data science. So let's say we want to create some array of integers, let's call it nums, and we want to have the numbers 1 through 5. So all we would have to do is nums, then we put brackets, then it's 1, 2, 3, 4, 5. And then we can print out nums, exactly as you'd expect, right? Very simple. You notice two things. A, we didn't have to define that we wanted to create an array, and 2, we didn't have to define the type of the array. The reasoning for this is because Python actually allows us to have arrays with multiple different types within a single array. So for example, if we want to create a new array, call it R, we wanted to have, I don't know, 4, 6.7, the word giraffe, and then, I don't know, true. So we have all 4 of like the basic types. Python has no issue with us doing this, and it'll, again, print out exactly as you'd expect. So yeah, there's a lot of flexibility when it comes with lists in Python. So yeah, I guess the other thing we should maybe talk about when it comes to arrays is indexing. So like most languages, Python indexes from 0. So if you wanted to print out the first element of R, all we'd have to do is reference R, bracket, 0, and that's going to print out 4. Again, not really many moving parts going on here. Pretty much as you'd expect in any other language, Python keeps it pretty simple. The size of the arrays is dynamically allocated. So if you want to add another value to R, say you want to do r.append, let's say, I don't know, blue, then we print out R again. So I guess we appended it twice. But yeah, there's a lot of flexibility when it comes to arrays in Python, in terms of not only the type, but also how the list behaves, and how it's declared. So very hard to go wrong with arrays in Python. There's a lot of room for flexibility. The other data type, or rather the other data structure that we'll talk about, is Python dictionaries, which in every other language apart from Python is just referred to as a hash map, right? So think like key value pairs. So you have some key and you want to map it to some value, or some list of keys that you each want to map to a value, right? Again, so the way that you declare this is pretty simple. So let's say that we wanted to make a hash map with some information about a specific course at UCF, right? So we'll go ahead and call it course. We'll assign it. And the way that you sort of indicate a hash map or a dictionary in Python is just by using these curly braces. And you can hit enter. You can also keep it all in one line. Typically, most people like to keep it separated out like this. It looks a little bit cleaner. But again, it's not super relevant. And the way that you go ahead and declare this is that we can first create our first key. So let's say we want, since we're making it a class or course at UCF, maybe we can start with name. So we'll create a string called name, and that'll map to another string, let's say stat theory 2. And then we'll separate the next field by commas, right? So we have the name of the course, maybe we want the code of the course. So maybe that should be an integer. So stat theory 2, I think is 4322 is the course code. That could be wrong. No, that's not wrong. And then let's maybe also include, like, I don't know, the department, and that should of course be statistics, right? And then if we print this out, then we'll go ahead and get the dictionary with those key value pairs that you expect. And if we want to access like the course code for a specific course, then we would index it exactly as we would with an array. So we say course bracket, course bracket, and then we'll go ahead and include the key that we want to access. So in this case, we want to access code. That'll return 4322. So yeah, again, Python dictionary is super flexible. The types that you're including in here can be mixed types. You see that, I mean, I guess all of the keys that we use were strings, but they don't need to all be strings. And then the value pairs, we have 2 strings and integer. Again, doesn't need to be declared at any point. A lot of flexibility there, just very similar to lists. So yeah, very simple to go ahead and use, and very efficient for storing that type of key value paired data. But with that being said, we can go ahead and talk a little bit about functions, loops, and conditional statements in Python, which, as you might expect, are relatively simple compared to other languages. So let's talk about functions first. So if you've worked with, like, I don't know, for example, let's talk about Java. If you want to create a function in Java that adds 2 integers, what that would sort of look like is int sum ints, and that takes in an int a, int b, and then we create then we have the logic of the function inside of it, right? So I want to bring some attention to this method signature. So the first thing that we're doing is declaring the return type of the method, which in this case is an integer. Then we have the name of the method, and then we have our two parameters, which we again have to specify the type of the parameters that we want to accept. As you might expect, in Python this looks a lot different. So if we want to create this same function in Python, all we have to do is use this keyword def, add ints, and then a and b. So you'll notice here we don't have to specify a return type, because again, Python kind of figures that out on its own at runtime. And again, we don't have to specify the types of our parameters, right? So we have an integer in A and an integer B, but we don't have to explicitly say that those are integers. And the way that we go ahead and show that this is the end of our statement is by using a colon, which you'll see is a pretty common pattern throughout all of Python's functions. And then we can go ahead and implement the logic. So in this case, it'd be like we have some result equals A plus B, and then we'll go ahead, and return res. So again, very simple. You'll notice that we don't have curly braces like most other languages do. So instead of using curly braces, we dictate ownership by the indentation. So in this case, we have this function, def add ints, and then we have the logic one indentation more to the right than the function declaration. So if I add down here another piece of logic, let's say print, I don't know, we can just write hello world again. This doesn't belong to this function because it's one indentation to the left, right? So it no longer belongs to that function. But if I were to go back and then tab it one in, now this belongs to that function, right? So this is a design pattern that you see pretty frequently in pretty much every language. Even languages that use curly braces typically also do indentation just for stylistic reasons. So Python just removes the curly braces and basically just uses the indentation as both a stylistic choice as well as a functional choice, right? It's dictating the ownership of the function or the conditional, as we'll see. So yeah, that's something to keep in mind. So you want to be careful about the tabs that you're having, the amount of tabs that you have in front of all of your statements. You'll run into errors if you have any issues with that or do something incorrectly. It'll be very obvious to see what you've done wrong. So you'll probably run into that many a time in your Python career. So yeah, now we kind of briefly talk about functions. We can go ahead and talk about loops. So in this workshop, we're kind of only going to talk about for loops. Also, obviously, Python also has while loops. Those are more scarcely used in data science purposes. So we'll stick to for loops for now. So the main reason that the main purpose that you'll find yourself using for loops in Python is for iterating over some data types, right? So think that you want to iterate over a list and you want to print out all the values of the list. One way that you can do that is by using the Python built-in iterator. What do I mean by that? So when you use a language like Java or C, the way that you'll write a for loop typically, if you're not using an iterator, is you're writing something like for int I equals 0, I less than length of nums, I plus plus, right? And again, you're going to be using those curly braces. So that's sort of how you'd expect the logic to look like. And Python does have an equivalent to this. And what that looks like is doing for I in range. Let's go ahead and write 0 to 5, print I. So as you'd expect, this prints out 0, 1, 2, 3, 4, but it does not print out 5. The reason for this is because we use this range function. What this is doing is it's giving us an iterator from some specified lower bound to some specified upper bound. It's important to keep in mind that the lower bound that we're specifying is inclusive, whereas the upper bound is exclusive. So 5 is not in our iterator, but 0 is in our iterator. So slight nuance there you have to keep in mind. But yeah, typically when you're iterating like over a list in Python, this isn't the method you'd want to use, as there's slightly more elegant ways to do it. So for example, we have that list nums from earlier, so which is 1, 2, 3, 4, 5. Let's say that we want to iterate over that list. The better way to do that would be doing something like for I, or maybe for num in nums. So what this is saying is we're iterating over this list of nums, and then for each value, over the list, we're creating an iterator. So for each step in our for loop, we'll go ahead and assign this value num to whatever the value at our current time step is in our loop. So if we print out num in this for loop, we'll see that it prints out each value in this list, right? So we go through the first iteration, we're going to see that the value is going to be 1 at the first point in our iterator. So we'll print out 1, we'll go through, num gets reassigned to the second value in nums, which is 2, we print out 2, and so on, right? So it's a pretty, it's typically an easier way of going about printing, or rather iterating over some sort of data structure that you already have defined. But yeah, multiple ways to go about doing that. And then if you wanted to use this original approach, you could do, or the approach that is a little bit without using the iterator. You can still do that. So what that would look like is you can do for I in range, and then you can write the 0. This default lower bound is always going to be 0, so you actually don't need to write it out explicitly. And then so you can just write the length of nums, right? Because you're going to be going from 0 to the length of nums. Because even though we're using zero-based indexing, since the upper bound is exclusive, we're now actually going to be accessing that index, right? So we don't have to subtract 1 from that. And then we can print nums, and then we just have to access the index at I. This is going to give us the same output, just a different way to go about doing it, just to show that there's multiple ways to use for loops. But yeah, something to keep in mind. But yeah, relatively easy. And yeah, just important to keep in mind for this range function that this upper bound is exclusive. That being said, we can talk a little bit about conditional statements. So again, conditional statements will follow a very similar type of syntax. If you've used any other language, it follows a very similar design pattern. So let's say we have some integer x assigned to 3. And let's say if x is greater than 0, we'll print out x is greater than 0. And then we can use else if statements. So the way that you sort of define else if in Python is if and then your statement. So let's say x is equal to 3. Then we can say print x is equal to 3. And then else we'll say we'll print out that x is not equal to 3. Okay, cool. So if we assign this to any other value, maybe we should change this to less. That might make a little bit more sense, right? So we'll say x is less than 0. So in this case, it's equal to 3. So then we can say else x is greater than 0. Cool. So in this case, since x is equal to 3, we're going to print out that x is equal to 3. If we change to x to some negative number, say -5, then we get x is less than 0. Then if we change it to any positive number that isn't 3, we'll get x is greater than 0, right? So very simple, kind of the same design paradigm. Again, just be careful with the indentation, as that's something that's a little bit more critical in Python than is in other languages, right? But yeah, I guess with that being said, we can go ahead and talk a little bit about pandas. So if you're unfamiliar with what pandas is sort of the premier data loading and data manipulation library in Python. It's built specifically or mainly for tabular data, and it's something that is pretty widely used. I mean, 90% of cases in which you're doing EDA, or no, 99% of cases in which you're doing some sort of exploratory data analysis in Python, you're going to be using pandas to some extent. And if you're not using pandas, you're using a library that's built on top of pandas. So with that being said, very important library to get very well acquainted with, right? So the first step in using pandas is first to import it, right? So the way that you go about doing that is you write import pandas as PD. So we go ahead and run that, and then we get it imported. So what is this statement actually doing? So we're importing the library, and then this as PD part is saying that we want to import it, but we want to be able to reference it by this keyword PD. And instead of having to write pandas dot and then whatever function, we can just write PD. This is pretty standard throughout all of data science. You'll never see someone not using this as PD part. I don't know why, but just do it. There's not really much rhyme or reason apart from it's just a little bit more convenient, and it's conventional with everyone else is doing. But yeah, a quick side note, if you're working locally on your machine and you don't have pandas installed, or for some reason you're on Google Colab and it doesn't have it installed, how you can do this, how you can install it directly from your Jupyter Notebook is writing !pip install pandas, and then you can run that. You can also just do this in your terminal without the exclamation point. But yeah, this allows you to do it straight from the Jupyter Notebook. You'll see it's already satisfied for me because I already have pandas installed. Yeah, if you're in Google Colab, it should be automatically installed. But yeah, so with that being said, we can actually go ahead and start using pandas for its main purpose, which is data loading. So before we actually load the data, we want to make sure that we have the data in our environment. So you'll see here, we don't really have anything in our Google Colab directory. So we'll go ahead and import it using this button up here. And you'll see that in the zip file, we have this housing CSV file we talked about earlier. So we'll go ahead and open that so that it's in our directory. Cool, and you'll see that popped up here. So if we want to use pandas to load in a CSV file, it's very easy. All you have to do is assign it to a variable. We'll call it df, and we'll explain why we use that name in a moment. Equals pd.read_csv, and then we'll pass in the path of our data that we want to use. Because our data set is already in the same directories we're working in, all we have to do is pass in the name of the data. So it's H housing.csv. We'll go ahead and run that, and we have that loaded. The reason we use df here, when we're using the pd.read_csv function, we're importing the CSV as what's called a pandas data frame object. So what a pandas data frame is, it's an object that's built inside of the pandas library that allows you to use all of the panda functions on that particular data set, as well as functions from other libraries as well that are built upon the pandas library, right? So df is just short for data frame. It's sort of just the conventional name that pretty much everyone uses. Again, a lot of the stuff you'll see, a lot of the naming conventions are very standardized, and it's typically best just to follow it, just to keep with a convention, right? But yeah, after going ahead and importing that, we can actually go ahead and visualize some of our data set by doing df.head, and we'll pass in a number, let's say 5. So what this does is it shows us the first 5 values in our data set. So the data set that we're using today is a pretty standard data set. It's sort of like the hello world of regression data sets, right? So you'll see 13 different columns here. So you'll have price, area, bedrooms, bathrooms, stories, etc. So functionally what this data set is primarily used for is building machine learning models that take in parameters like the area of a house, the amount of bedrooms, the amount of bathrooms, etc. And your objective is to project the price of the house given those parameters, which we'll go a little bit more into later. But just to know that that's what our data is sort of composed of in this example. Great. So we can go ahead and do some preliminary sort of data exploration pretty simply in pandas. So the first thing we can do after we do df.head is we can do df.shape. And this gives us the dimension of our data set. So you'll see 545 by 13. So what that means is that this 13 is showing us the number of columns that we have. So we have these 13 columns. So we have price, which is what we're trying to predict, and then we have 12 features to try to predict that. And then we have 545 rows. So each of these rows is one instance of our data set, right? So in the context of our data set, each of these rows is one house that we're trying to predict the price of. So we have 545 of them. So yeah, that's good to know. And then we can go ahead and do the next thing, which would be df.columns. Obviously, the columns are very clearly displayed here, but having a list of them is useful not only for our own understanding, but a lot of functions will require us to pass in a list of the columns that we want. This is a very easy way of doing that. So this is a pretty good preliminary step. And yeah, now we can go a little bit more into understanding our data a little bit deeper. So the next thing we can do is df.info. This is going to give us some more information about our specific parameters that we're going to be using. So we have all of our 13 columns that we have in our data set. We'll have the name of the column, the number of non-null rows within that column, as well as the data type. So we saw earlier when we did df.shape that there's 545 rows. All of these columns have 545 non-null values. So there's no missing values in our data set, which is great and something that's never going to happen in the real world. We're not really going to be talking about data cleaning today, so that's why we chose this data set, but just know typically that's going to be the next step in your exploratory data analysis. But yeah, good to see that we don't have to deal with that here, right? But yeah, so that's typically the next step that you'd want to do. And then something else we can also look into is df.describe. Describe. And very similarly, this is going to give us some more information about our continuous variables, giving us the count, mean, standard deviation, etc. This just gives us some more sort of higher level information about our data set without having to actually do any computation ourselves. This can be useful in a lot of instances. In the context of this data set, this probably isn't super critical, but it's nice information to have, right? But yeah, with that being said, we can go ahead and talk a little bit more about data selection. So what this means is typically we have this big data set. What if we want to select only certain types of data or data is within certain ranges? That's typically something we'll have to be doing to some extent when we're working through our EDA. So how do we do that with pandas? So it's pretty simple. The first thing we can do is we can index pretty much exactly like how we indexed our arrays earlier, but instead of using a numerical column, or sorry, a numerical index, we can reference by the name of the column. So for example, we can do df and index at the price column, and this is going to give us a list of the prices. And you see that there's also this additional column for the index. This is something that we have to be a little bit careful of when we use it later, which I'll point out once we get to it. But yeah, essentially it's giving us a list of all of the prices from our data set without the rest of the features in our data set, right? And we can actually go ahead and take this a step further, right? Because maybe we don't just want like the price or the one column in our data set, but we also want to do some filtering, right? So one way we can do that is we can do like df at bedrooms, and then we can say like greater than 3. So what this is giving us is a list of an index list of all of the values in our data set, or sorry, all of the rows in our data set, with a Boolean saying whether or not there's greater than 3 bedrooms in that specific house, right? So this is pretty useful, but just having a list of Booleans probably isn't super significant to us, right? So maybe we want to take this a step further, and there's a really easy way to do that. Since it's giving us an index set of Booleans, we can actually go ahead and pass this right back into our data frame and get some slightly more useful information. So if we wrap this all in another, if we do df at this index, so this is essentially calling our data frame and passing in this list of Booleans, and it's going to return us an instance of our data frame with only the values from that list of Booleans that are equal to true, right? So within the context of what we just did, it's giving us a list, it's giving us an instance of our data set where we only have the houses where there's more than 3 bedrooms, right? So this is pretty useful information to have, and it's something that can use a little bit more extensively. So let's say that we want to do this for maybe 2 different qualifiers, right? So maybe we want to have df at, maybe we want to have df where the number of bedrooms is equal to 3, and we want to have df with the number of bathrooms is greater than or equal to 2. So what is this giving us? This is giving us an instance of our data frame where we only have the houses that have exactly 3 bedrooms and greater than or equal to 2, we have exactly 3 bedrooms and we have greater than or equal to 2 bathrooms. So yeah, this gives us some pretty easy data manipulation, kind of helps us do some more controlled selection that we might have to use sometime when doing our EDA, right? But yeah, that's pretty good to have. And with that being said, we can go ahead and talk a little bit about grouping and aggregation, which is another super critical and very commonly used methodology when we're doing preliminary data analysis. So let's say we want to do, we have this function in pandas called df, and then we call group by. And this allows us to do essentially bucketing by some metric, or rather by some column or some type of grouping in our original data set, and we use some metric to sort of create subgroups from that group. Again, this is a little bit more difficult to describe, but maybe this is a slightly more easy way to demonstrate it. We can say group by the number of bedrooms, and then we'll give it at the price, and then we'll say dot mean. Let's see what this gives us. oops, bedrooms. It looks like I misspelled that. Okay, so you'll see that this gives us the mean price of the house for each of the number of bedrooms. This value doesn't really mean much to us because it did some weird rounding, because Python can sometimes do that. One way we can get around that is we just write dot round, and we can just round to 0. So yeah, this gives us the average price of the house for each number of bedrooms. So for the houses that have 3 bedrooms, the average price is this number, right? So that's really helpful, as it allows us to do some pretty good grouping and bucketing, which is something that we have to do very often, right? Might give us some insight as to what features we want to be using, what's sort of significant to determining what the price of the house may be. But yeah, what might be slightly more important is to sort of visualize this, which we'll do when we talk about the visualization library in just a moment. But yeah, this is a pretty good way to get some intuition about some grouping in your data set. And then one more function that I'll talk about in pandas is df.sort values. As the name sort of implies, this allows you to sort of sort your data frame by some metric. So let's maybe you want to sort by price. We'll set ascending equal to false so that the highest price is at the top. And then we'll go ahead, and print out the head, and we'll print out like the first 10 values. This is going to be the 10 most expensive houses in our data set. So again, gives us a really way to sort of manipulate our data, get a little bit more insight without having to do a lot of the heavy lifting, right? So sort of cuts out a lot of that. But yeah, the next thing we can talk about is some matplotlib basics. So if you're unfamiliar with what matplotlib is essentially like the super fundamental data visualization library in Python that's used in pretty much most to all scenarios. The cases in which you're visualizing data without matplotlib, typically you're using some library that was built on top of matplotlib, right? So it's going to look very similar either way. So it's a very critical library to get a very good and deep understanding of. So we'll go ahead and introduce some of the basics, but just know this is even scratching the surface of what you can do with this library. But yeah, we'll go ahead and get into it. So again, the first thing before we can actually start using the library is importing it. So the way we do that for matplotlib is import matplotlib.pyplot as plt. So you'll see that we use a matplotlib.pyplot. We're functionally importing a module from matplotlib. Again, not super important what this means, but just to kind of explain that, so at least you've heard the terminology, right? So we'll go ahead and import the library, and then we can go ahead and do our first plot. So maybe for this first plot, we want to plot a bar plot for average house price by number of bedrooms, which is exactly what we were doing here in this bucketing example, right? Except now we just want to display it visually as a bar graph. So how do we do that? So the first thing we want to do is we want to call the plt.bar function, and this is just going to create a bar graph given some data. So how do we pass this into our function? So the first thing we probably want to do, even before we define this, or rather call this function, is define a variable. So maybe we want mean prices by bedrooms equals df.groupBy. We'll add the same thing that we did here, and we'll just assign it to some variable. So bedrooms at price dot mean, and we'll go ahead and round that to 0 again, so that we can make sure that our numbers look somewhat clean and we don't have any weird Python rounding. I ran that by accident. But yeah, so we have that variable defined. So we'll go ahead and pass that into our bar graph function. So we can mean prices by bedrooms dot index. The reason that we're doing this is you can see when we call this function earlier, which I kind of pointed out, we have not only the values themselves, but also the index. So we can access both of these individually by referencing them specifically. So we can write dot index is going to give us, as you can imagine, the indices, which in this case is the number of bedrooms. And then for the other value that we want to pass into bar graph is we can write mean prices by bedrooms dot values. And what this is doing is, as you can probably imagine, is giving us this column, which is the prices. So the values is going to be our prices in this case, and the index is the number of bedrooms, which are the two axes at which we want to build this bar graph around, right? So that makes some amount of sense. And then before we want to plot this, let's add a title to our graph as well as both of our axes. So maybe we can write plt.title average house price by number of bedrooms, and we'll name our X label as number of bedrooms, and then we'll go ahead and write plt.y label for our y-axis as average price. In this case, it's going to be in millions, so we'll go ahead and write that, and then we'll write plt.show. And if we go ahead and run this cell, you'll see that we get this bar graph of our the data that we had from here earlier. So this is going to be the number of bedrooms as well as the average price in millions. So if we analyze this, we can see that typically the number of bedrooms indicates some amount of increase in price, unless there's 6 bedrooms. I don't really know why. But that's interesting, I guess. But yeah, so that's a really easy way to go ahead and visualize this. Surprisingly small amount of code to get a really powerful visualization, right? So that's sort of the power of matplotlib. But obviously we're not bounded by bar graphs. Maybe we want to plot a scatter plot, which is sort of the conventional sort of first thing that we'd want to do with the data set like this, right? So how do we go ahead and do that? So we can use another function, plt.scatter, obviously for scatter plot, and we can go ahead and pass in df at area. Let's say that we maybe should write a comma to label this. Maybe we want to plot house price versus square footage. So how much does a house cost by the square footage, right? Probably some important insight for us to know for given the context of this data set. So we have df at area, so that's going to be our first axis, and then we'll have df at price. And we notice that obviously a lot of the numbers for the price in our data set got very high into the millions, right? I think when we looked here, yeah, 13.3 million was our most expensive. So we probably want to do some scaling to make this plot look a little bit more interpretable, right? So maybe we want to divide this by 1 million. So one way we can do that is just by dividing it by 1 million. And then the reason that I use the underscores here, by the way, if we just put 6 zeros together, it's probably gonna look a little bit hard to read. So that just allows us to differentiate a bit, but this is just a million. So plt.scatter, and then we'll do plt.title. And then again, it's just gonna be house price over square footage. And then we'll label the x-axis as square footage. And then plt.y label for our y-axis as price in millions. And then we'll go plt.show. Cool. So if we go ahead and run this cell, great, we get a nice little scatter plot showing the square footage by the price, which is super helpful in this case. We notice that there's a lot of clustering though. So maybe there's some modifications we can make to some of our parameters to allow us to make it a little bit more easy on the eyes, right? So in this plt.scatter function, there's a parameter called alpha. So this value will automatically be defaulted to 1. So if I run the cell again with alpha equals 1, it's going to be exactly the same. We can but this is the transparency parameter. So maybe we can play around with this to make it look a little bit nicer. So if we set this to like 0, we'll see that obviously since transparency is 0, it's going to be fully transparent. We can't see. Maybe if we set it to like 0.5, yeah, we can see that this data is going to look a lot nicer because we have that clustering still. Because the clusters of the transparent data sort of aggregate together and make a darker color, it makes it a little bit more clear that we have some very heavy concentration here, right? Which makes our data slightly more visually interpretable, which is what we want, right? So yeah, that's a helpful little parameter that we can play around with. Obviously, there's a lot more parameters in all of these plotting functions, so I encourage you to explore what you can play around with and see what you can make happen in your plots. But yeah, maybe we can plot one more plot in this section. Let's maybe do a histogram for price by the number of houses in that price range, right? So histograms obviously are going to be a pretty helpful tool to be able to visualize and get some more insight about our data set. So we'll go ahead and use the plt.hist function for histograms. We'll go df at price. And then obviously, since we don't have another feature as another axis, we'll go ahead and have to define the number of bins that we want. Obviously, maybe we'll go ahead and scale this again by 1,000,000. Then we'll define bins equals, let's try 30. And then we'll go ahead and define the edge color as black. And this is just going to define the color of the outline of the bars in our histogram. Just makes it a little bit easier to see this way. But again, we'll go ahead and add a title, histogram of house prices. And then we'll do X label, yeah. We'll go price in millions. And then the y-axis here is just going to be the frequency or the number of houses, right? And again, we'll do plt.show. Give that a minute. Oh, I misspelled X label. Oops. Okay, great. So this looks great, but obviously since we have a lot of bins, maybe it'd be nicer if we could increase the size of this plot so that it's a little bit easier to see. So one way that we can do that in matplotlib is we can do plt.figure, and then we can pass in a parameter fig size equals, let's say 10 and 6, or 10 by 6. This is going to make it a little bit bigger. You can do this for any of your plots. You can make them whatever size you want. 10 by 6 is pretty standard, and then I think 8 by 4. I don't remember exactly what it is. But yeah, we have this nice little histogram. We can see that we have a pretty skewed distribution, which is kind of what you'd expect when it comes to house prices, right? But yeah, this is a pretty great visualization, gives us some great insight for our data. And yeah, I think that's pretty much it in terms of what we were going to cover today for matplotlib. So that being said, we can go ahead and talk about the last library that we're going to be covering, which is my personal favorite, which is NumPy. Fun fact, I actually named my cat after this library. That's a story for another time. So to first sort of motivate why we use NumPy, I'm going to draw some distinct differences between the lists that were defined in native Python and the lists that are defined in NumPy to sort of explain why we use NumPy, what it does differently, etc. So if we have a list nums equals 1, 2, 3, 4, 5, so just obviously a list of integers. In native Python, if we do nums times equals 2, which is multiplying this list basically, which I know seems a little weird, but there is some significance to that. If we go ahead and print this out, you'll see that once we multiply it, instead of multiplying each of the values individually, it'll sort of copy the list and append it onto itself. This behavior isn't necessarily bad, right? There are some instances in which this is the exact behavior that we want. But there's a lot of instances in which this is not behavior that we would want, right? So to sort of show the difference between how that works and how NumPy works, let's go ahead and create the same array in NumPy. So again, we'll go ahead and first import NumPy. So we'll do import NumPy as np. And then we'll create that same list, nums, let's call it nums underscore np for clarity, equals np.array. And then the way that you define arrays is exactly as you would in native Python, except you wrap it in this numpy.array. Oops, I forgot 3, 4, 5. You wrap it in this np.array function. So inside here, we just define a normal array, and then we're wrapping it with this. If we print this out before doing anything to it, again, prints out pretty much exactly how you'd expect an array to print out. Visually looks exactly the same. But if we were to do this nums times equals 2 thing again, and then print out nums underscore np, you'll see that instead of duplicating the array and appending it, what it actually did was go through each of the values in our array and multiply it by 2. So a very distinct difference here is that NumPy is actually applying the operation element by element as opposed to applying the operation to the entire object itself. This is a very important distinction in behavior. Obviously, there's use cases in which you want both of these to happen, but it's something to understand that NumPy is applying these operations element by element. Where's a use case that we might want to use this to create some sort of increase in efficiency, or what is a use case that we could actually use this in to some meaningful capacity, right? So that we had some list, let's call it scores, np.array, and let's just fill it with some scores that are close to like 100, right? So we can write like 85, 97, or 85, I guess I wrote, okay, and then we can write like, I don't know, 67, and we can write 89, and then like 90, right? So we have this list of numbers. Let's say that we want to normalize this list, right? And let's create some z-scores. So we can write normalized is equal to scores. I hope most of you are familiar with this formula, minus scores dot mean, and divide that by the standard deviation. Dot std, and then print out normalized. Okay. So we have this normalized list, and it's exactly how we saw it in this other example. This operation is applied element by element as opposed to the list itself, which is a really important distinction. And here we can kind of see an applied instance in which that is actually really important, right? And this mean and standard deviation function are both functions that are native to NumPy, and we can apply to any NumPy array regardless of dimension. So again, we have some very useful properties in getting some sort of meaningful data out of that, right? But yeah, apart from just creating like normal one-dimensional arrays, what we would actually like to use NumPy for is to do some linear algebra, right? So if you haven't taken a linear algebra class before, or you're unfamiliar with matrices and any sort of like applied math or statistics context, that's totally fine. We're mostly going to be talking about the very applied and Python focused way of doing this, and we're not really going to talk about a lot of the underlying math behind it. But to sort of motivate why we would like using NumPy specifically for matrix operations, NumPy is built is built in another language called C++, which, if you're familiar with C++, is a very fast language, specifically for operations like doing like simple floating point operations like addition, multiplication. C++ is very, very hyper efficient. Python, in its native form, is very, very, very slow at those operations. So if we have a library that's built upon doing very, very fast operations, and we want to use it for linear algebra, which is when we're doing especially like matrix multiplications, matrix inverses, you name it, we're going to have to be doing a lot of very fast, a lot of parallelized floating point operations. When it's built in C++, that's very, very helpful, right? As if this were built in Python, it would not be usable, right? So that's sort of the motivation as to why NumPy is such a standardly used library within the context of machine learning and linear algebra. But yeah, if we want to create a matrix in in NumPy, it's very similar to just creating a one-dimensional array. So we call a new matrix, and we'll just define it as matrix, equals np.array. And then again, we just wrap it in this function. And then we're going to define it just as we would a two-dimensional array. So maybe we want this to be 1, 2. And then the second row we just want to be 3, 4. And then we go ahead and print this out. Matrix. Cool. So you see we have this two-dimensional matrix, 2x2 matrix specifically. Yeah, that's all you need to do to define it. Again, very analogous to how you define just an array in Python, except we're wrapping it in that NumPy array function call. So extending from just defining an array or a matrix, we very likely want to also do some operations with matrices. Specifically, the first thing we want to do is matrix multiplication, right? So I wrote some logic code for a visual example here. Let's say that we want to multiply two matrices, 1, 2, 3, 4, and 5, 6, 7, 8. And I explicitly showed how that works for those of you who haven't been exposed to linear algebra before. But our output should be this 2x2 matrix, right? Because if we're multiplying two 2x2 matrices, the output should also be 2x2. So let's say that we want to multiply these two matrices. So first of all, we should probably define these two before we do anything else. So we'll define this first one as np.array, and it's going to be exactly as the one that we defined earlier, but we can go ahead and just define it again. 3, 4, and then we have a matrix B, np.array, 5, 6, and then 7, 8. Great. So we have these two matrices, A and B. So if we, maybe we can just print these out, A, B. Oh, sorry. Oh, right, okay. There's some other logic I have to do. Oh, wait, I think I just forgot. Yeah, be careful about your brackets. Great. So we have these two matrices, A and B, which we can see here. How do we multiply these two matrices together using NumPy? So it's actually very easy. There's a few different ways of going about it. So the first way to do is np dot A and B. So kind of gives us the same output that we have in this example. Similarly, you can just use np.matmul. I don't know why they have two different, these are the same function. I don't know why they have two different names. But the way I typically find myself doing it most often is that NumPy actually gives us a really easy way to do this using an operator. So if we write a @b, you'll see that this gives us the same output. So as opposed to having to wrap it in a function call, we can actually just use this operator just as we would any other operator within Python, right? So like, this is pretty much analogous to how you do like multiplication between two integers in Python, except these are two matrices that you're doing a matrix multiplication on. So yeah. Pretty elegant shorthand. This is typically how I find myself doing it most of the time, but whatever way you find yourself most inclined to, you have my full support, man. But yeah, and the next thing we probably want to do after doing matrix multiplication is finding a matrix inverse. For those of you who haven't had a lot of exposure to linear algebra, again, a matrix inverse is for a matrix A is some matrix that we can multiply A by that gives us the identity matrix, which is basically a matrix with ones on the main diagonal and zeros elsewhere. So the algorithm to find the matrix inverse is actually relatively complicated, but fortunately NumPy handles that all behind the scenes. I do want to leave a little bit of a side note here. We're using this on very large matrices, like excessively large matrices is very likely not going to work. Because the algorithm used to find matrix inverses is, I think, in the big O of n cubed in terms of computational complexity. So you can imagine that it's depending on the size, or the computer that you're working on, it's not going to happen. But fortunately, we have a 3x3 matrix example. It should be more than doable. So let's first define our matrix A as, great, it actually already did the autocomplete for us. So it's going to be 1, 2, 3, 0, 1, 4, 5, 6, 0. And in order to find this matrix inverse, we can define a variable a underscore inverse. We'll go ahead and set that to np.linalg.inv of a inv. We'll see that the output here is exactly what we saw up here. And if we wanted to verify that, we can go ahead and do a underscore inv. And we see that the output here is the identity matrix. You'll notice here that for some of the columns that should be 0, we get numbers that sort of look like this. So for example, we have negative 2.664 blah 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 e negative 15. So the reason that we get these is because Python has some floating point arithmetic that it's doing behind the scenes, and because floating point numbers on a computer can only be represented with so much accuracy, Python in a lot of cases will have some slight approximation errors. This is a number that's infinitely close to 0, so it's like what? 0.14 zeros 2664, right? So it's excessively close to 0. But it's not quite there, but just to explain why that's happening. But yeah, we verified that this does work. You'll notice here in this function call, instead of just doing np.inv, we have to do np.linalg.inv. The reasoning for this is because the inverse function actually doesn't exist in the Python library, but exists in a module called linalg inside of the Python library, inside of the NumPy library. Slight distinction, no real practical application there, but just important to remember. Some functions exist just in NP and just in NumPy. Some of them exist in separate modules inside of NumPy, and that's pretty consistent with other libraries as well. Something that you just have to keep an eye out for, unfortunately. And then the last thing we'll talk about is matrix transposition. So for those of you who haven't taken linear algebra before, the transpose of a matrix is essentially just another matrix in which the rows of the original matrix become its columns and the columns become its rows. Excuse me. So in this first matrix, our first column is 1, 0, 5. So we'll see in the transpose version, 1, 0, 5 is our first row, but then conversely, 1, 2, 3 is our first row in the first matrix. So the first column in our transpose matrix is 1, 2, 3. So if we want to find the matrix transpose in NumPy, fortunately, it's very easy to do. All you have to do is I guess it's the same matrix we had to find here already, right? Yeah, 1, 2, 3. Yeah, it's the same thing. All we have to do is write a dot capital T for transpose, and that'll give us our transpose matrix. Very simple to do. Again, NumPy does a great job at making the shorthands very elegant, so we don't have to worry about writing too much boilerplate, which is great. So yeah, the last thing we'll do is we'll go ahead and tie all the concepts that we went over together. And we'll do that by fitting a regression line to our data set using the normal equations. So if we go back up to that scatter plot we made, we'll notice that we have this data set and two of the features that we have are the house price and the square footage. Maybe something we want to try doing is seeing if we can create a machine learning model that uses the square footage of a house and uses that to try to predict the price of that house, right? And maybe there's some sort of linear relationship there, right? Looking at the scatter plot, the linear relationship looks like it probably isn't the strongest ever, but it looks like there's maybe something there, right? If we have a line, if you're following my cursor, maybe something like this can give us a somewhat accurate estimate of what the price of a house may be. In the real world, we'd probably want to run some assumption tests and maybe look into some transformations here. For the sake of time, we're not going to do all of that in this video, just so we can show you the practical applications of Python as opposed to the full methodology. But yeah, one way that we can go ahead and do this is using linear regression and solving the normal equations. So the way that we want to create that straight line, we can define that very explicitly. If you remember slope-intercept form, essentially we want something that sort of looks like y equals mx plus b, right? So the notation that we use in statistics is y equals beta 0. So that's going to be our intercept term. So basically the b and y equals mx plus b, right? And then plus beta sub 1. So that's going to be our m and y equals mx plus b. And then x, which in the context of our data set is the square footage of the house. So given the square footage, if we multiply the square footage by some number beta 1 and then add some number beta 0, that should give us some estimate of the price of what that house should be, right? So the only issue is we have to find what values should be our beta 0 and beta sub 1. There's a lot of different ways to do that, but fortunately, there's a very elegant closed form, oops, didn't mean to open that, called the normal equations, which look like this. So beta, which in this case is a vector containing beta 0 and beta 1, is equal to the inverse of x transpose dotted with x, and then that is dotted with x transpose dotted with y. I won't go very deeply into the mathematical formulation of this, but just know that this is going to give us essentially the optimal values of beta in terms of MSE. This is going to give us beta that minimizes the average squared error between all of the values in our data set. So how do we actually go about writing this in code? Well, the first thing we have to do is take our data frame that we made in pandas and turn that into an x and y vector. So the way that we go about doing that is we'll assign some variable x to be equal to df. So we want the square footage, right, which is under the area column in our data set. And we'll go ahead and extract the values, right? We talked about earlier, it's going to give us essentially two columns. One of them is going to be the index and one of them is going to be the values. We don't really care about the indices. Since we're doing matrix multiplication, we don't really need them. So we'll go ahead and take the values. And similarly for y, it's going to be df at price dot values. So we can go ahead and print out x and y. Again, this is going to kind of give us a bunch of garbage. We don't really care about this, but just to show that we did assign those variables correctly. But yeah, one more thing that we're going to have to do before we can do any matrix operations is we actually need to add one more column to the x matrix, right? The reason for this, in our closed form here, we have y equals beta 0 plus beta 1 times x. So the way that we have it set up right now is that all that x has is the square footage of the houses, right? But that gives us something to multiply for our beta 1 term, but that's not giving us anything to multiply for our intercept term, our beta 0. So we need to add another column of the same length that's just a bunch of 1s, right? That's going to give us something that we can use for our intercept term so that we have our full y equals mx plus b pattern, right? So the way we go about doing that is we can use x is equal to np.column stack. And this is basically, as the name implies, stacking another column onto our NumPy array. And we'll go ahead and add, and basically we're adding an array, right? So it's going to be np.ones. And we need to define the length of that vector, which is just going to be exactly the same length of x, right? So we can just pass in length of x. And we want to add that to, we want to append that with x. So that's going to give us this new let's maybe print that out too. So it's going to be exactly the same as this original x matrix, except we also have this ones column for our intercept term. Yeah, this is sort of standard practice with linear regression. So again, I know maybe not all super intuitive, but I promise once we get to the actual problem formulation here, it'll make slightly more sense in terms of the computation, right? So now we have everything set up. We can actually go ahead and follow the pattern that we had up here. So we can essentially copy this equation verbatim and basically write it in NumPy terms, right? So the way that we do that, we'll assign our parameters beta is equal to np.linalg.inverse of x.transpose dotted with x, right? Because that's going to be this first part right here. And then we'll dot that with x.transpose, and we're going to dot x.transpose with the prices of our houses, right? Which is y here. So if we go ahead and, oh, what did I do wrong here? Oh, wait, hold on. I think we have to click run all again. Yeah. Sometimes in Jupyter notebooks, if certain things were ran out of order, it'll cause some issues. So sometimes it helps to just run everything. But yeah, so we have our beta terms now. So we have beta 0 and beta 1 for our data set, for our data. But we want to use that and multiply that again by our original prices, or sorry, our original square footage. So we can get what our model thinks the price of each house should be given the square footage, right? And then we can use that to evaluate the efficacy of our model. So let's first get those predictions. The way that we get the predictions, we can assign some variable ypred is equal to x, and we'll dot that with beta. So we're going to multiply the square footage, the vector of the matrix of square footage in the intercept term by the weights that we have from solving the normal equations. So this is going to give us what our model's predictions are, which is great. But now we have to do some actual evaluation, right? So we want to get some metrics so we can numerically evaluate how good our model is. So we'll do some evaluation. When we do this evaluation, we want to use a library called sklearn. We're not going to talk about this library super extensively for sake of time, because we're only using it for metrics, but this is a pretty standard library for using metrics for evaluating your model. So we can do import, we'll use mean squared error, and we'll also use R2 score. Oops, R2 underscore score. So this is going to allow us to get 3 separate metrics that we're going to be able to use. So the first one is mean squared error. What does mean squared error mean here? So mean squared error is giving us the mean square distance between our model's assumption. So basically for each instance in our data set, what does our model think the price of the house is based on the square footage minus the actual price of the house for that instance. We square that. What's the mean for that value for all instances in our data set, right? So the way we do that, MS equals mean squared error y, and we'll also pass in our model's predictions. Another metric that we can use for regression is the root of mean squared error, which is something that might be slightly more useful here. So we can assign that as RMSE. Since it's just the square root, we can just do numpy.square root of the MSE. And then we want the R2 score. What is R squared? So what does R squared mean here? R squared is essentially giving us a percentage for how good our model is fitting our data. Slightly more complicated than that, but I won't go too deep into it. But again, it's pretty easy to compute that just by doing R2 score and then passing in y and ypred. And then we'll go ahead and print all these out. We'll use our f strings as we talked about earlier. So MSE. We can do the same thing for RMSE. And we'll go ahead and print out for R squared. So we'll do R squared, R underscore squared. Great. Print those out. So we can see here that our MSE is really, really high. We can maybe do some logical reasoning here. We know that most of the houses in our data set were in the millions. So if our model isn't fitting exactly on those prices correctly, our model is going to be pretty far off on a lot of those guesses. When we square that in, we're already in super high magnitudes. Our MSE is going to skyrocket. So we look at our RMSE, we can see that's slightly lower, but it's still pretty high. But maybe those aren't the best metrics. And we see our R squared is 0.28, which basically means that our model is again, this is an oversimplification of what R squared is, but we can, the very simple interpretation is that our model is explaining this data is 28% sufficient for explaining this data, is the very simple interpretation, which isn't great, but is maybe better than what these two scores sort of signify, right? But yeah, so the numerical understanding of how well our model performing is pretty great, but maybe we also want a visual explanation for how our model is performing. What does that mean in this case, right? So going back to the scatter plot, if we could visualize what line that our model is using is, maybe we can see how well it visually fits the data and why we're not exactly getting the best R squared, RMSE, and MSE scores, right? So we'll go ahead and plot that same plot again, and we'll add our line of best fit so we can sort of see how that fits in. So very similar to how we did before, we can actually just go ahead and copy this code from before, paste it right here. Again, we'll go ahead and do what we did for that last example. Oh, I forgot the second parentheses. We can do what we did for that last example and do plt dot figure. We'll pass in fig size, and again, we'll put it 10 by 6. Oh, sorry, fig size equals. Okay, so we'll get that same plot. And we'll go ahead and add an extra field here on plt.scatter. We'll go ahead and add a label, and we're going to call this scatter plot actual prices. We'll go ahead, I'll explain why we need the label in a moment. So we'll call this actual prices, and then we'll go ahead and add another call for plt.plot. And this is going to allow us to plot our line of best fit, so we can have that on top of our original graph. So we can write plt.plot, we can write df at area, so the square footage, and we can write ypred, and we can go ahead and again scale this for 1 million since we did that for the other variable, or sorry, the other axis. So scale that by 1 million. We'll give it a color. We'll make it red. I guess is probably the best contrast here since our dots are in blue. We'll assign a line width. We'll just make this 2 so it's easy to see. And then again, we'll add a label, and we'll call this predicted best fit line. Cool. So this looks good. One more thing we can do pretty quickly is just write plt.legend. And we can also do plt.grid. We'll set that to true. The reason that we're doing that is just that we can get this grid in the back, which might be helpful since we have that line. And then we also have this legend, which shows what everything in our graph represents, since we have multiple elements here. As we not only have the data plotted, but we also have this best fit line. So as I hinted earlier, this line seems to be fitting pretty okay visually. If you were to run the necessary assumption tests on this data set, you would see that a linear line is not sufficient here, unless maybe you do some data transformations. But again, that's not what we're here to do, right? We're really just here to go over the basics of these libraries in Python so you guys can get into your data science projects and sort of have a very baseline understanding of what to do. But yeah, as statisticians, I would hope that that was an alarm that went off in your head. But yeah, I think that's pretty much all that we had to go over in today's workshop. So I hope that that was able to sort of sufficiently give you guys the understanding of the basics of Python, as well as the basics of Pandas, Matplotlib, and NumPy. These 3 libraries are probably accounting for, I don't know, 70% plus of the work that you're going to be doing in most of your data science classes. They're sort of building upon the groundwork of everything else you're going to do. And the libraries that you're using that aren't those 3 are very likely libraries that are built on top of those libraries. So it's a very good idea to get as well acquainted to them as possible. But yeah, with all that being said, we appreciate you guys for tuning in. Feel free to leave your feedback below. And yeah, we hope to see you guys soon in our upcoming web series videos. And yeah, thank you so much for tuning in.